be hands together for our awesome session on Test Too Slow, Rethink CI with the one and only Simon Stewart. You probably know him, but if you don't, he is the creator of WebDriver and is the Core Slam 2 developer. He was the lead. I think he stepped away a little bit, but he still contributes along the way. And he was the tech lead of Google's web testing team, later browser automation, delivering web development APIs and infrastructure used by all Googlers. And he's an all-around awesome guy that's contributing to all types of projects. And I always love speaking with him and getting to have the pleasure of being here to witness one of his sessions. So welcome, Simon, to Future of Testing.
Thank you. Thank you very much. And how lovely to be here. And I only caught a few of the talks, but the ones that I've seen have been amazing with some fantastic speakers.
Yeah, absolutely.
So just phenomenal stuff. I'm now going to share my screen. Boom. All right. So yes, I'm Simon Stewart. I was the ex-lead of the Selenium Project. Still am the ex-lead of the Selenium Project. I'm an absolute build nerd. It's something that I've been really working in for quite a long time now. I used to be the tech lead at Facebook on their build tool called Buck and help them move toward a mono repo. So I love that stuff. If you are on any of the socials, Mastodon, Threads, those are the two that I am on most of the time. I am at SHS96C. You should be able to find me. So let's crack on with the talk. Now, before we begin, I think it's really important to say that, although I'm going to be talking about a specific example, the ideas are general. You can take these ideas that I present in this talk and you can apply them on any code base. But I am going to use one project as an example, and I think you can guess what that project might be. It's Selenium. Now, the reason for that is that it's an open source project. It uses these technologies and ideas that I'm going to be talking about. So you can grab that source code, you can have a look at it, you can figure out what's changed and what you like. But also because it's a project I know really well. But just remember that when you hear Selenium in this talk, you can think this could apply to my own project. So don't worry if you think it's super Selenium heavy. It won't be. It's going to be general ideas that you could apply to your own project. So why do we use continuous integration? I assume that for this audience, you are all familiar with the idea of CI. But why do we run it? Well, I always like to think in terms of feedback loops, particularly fast feedback loops. We want to know as quickly as possible whether a change is safe to make. So we use CI as part of that. We use it as one of our feedback loops. It lets us know that sort of when the CI build is green, there's a high probability that a change we've made is safe to put into production. It doesn't guarantee it. Nothing ever does. And we know this for a fact because, well, we still see bugs in production. So put another way, our CI builds let us know whether an incoming PR breaks any code or not, and so whether we can release it. And this is an example CI pipeline. I am sure this looks familiar to many of the people here. The first thing we do is we clone the repo, we check out the code, then we build it. We might sort of fan out a little bit and do linting in one node and run our small tests in another. And then once the small tests have started, we may start running some medium tests that need a little bit of infrastructure, but not much. And while that's going on, we might deploy to UAT or some Kubernetes cluster or something, so that eventually when the medium tests pass, we can then run the large tests. And those tests are normally the ones using a browser and stuff like that. And then once we're happy with that, we sort of fan back in and we do the deploy and upload. And, when the projects are small, this normally happens really, really quickly. It can happen in minutes to sort of tens of minutes. But I am also sure that everyone here has been in teams where that build time has extended out to hours and hours and hours. And, it's a problem because, as these stages start taking longer and longer and longer, these builds start taking longer, we waste so much time and we're more likely to go it's a red build, it's a failed build, but it'll be fine. So why do we do these kinds of pipelines. Like, why do we do that? Why do we structure our builds this way? And primarily, the reason is because when we make a change in our repo, we don't actually know what's changed. We've just got a PR. And so what we try to do is we have tried to organize our build to provide fast feedback loops. You'll see that we run the small test before the medium test before the large test. And we try and do linting off to one side. And the reason why we do that is because we want to know as quickly as possible whether something has gone wrong, but we're not entirely sure what we should be running. And so we just go like, fire everything, and we build whatever we can. And yeah, I mean, I guess that's great, but it's going to be confusing, right? So now that we've got like some context, let's take a look at how our CI build works. And I'm going to be taking Selenium as the example. So here are some numbers that I gathered from Selenium recently. It's a polyglot repo. There are lots and lots of different languages in there. And these are the top line numbers from a recent clone of the repo. You might wonder why we have everything in one place, and it's because we share a lot of code between the languages. In particular, everything pulls in little bits of JavaScript, and that's pretty handy to be able to get hold of that, make a change, and then run the tests that we need to. And lots of things depend on Java for their test as well, because we've got a lot of test infrastructure that we can spin up, and it will work kind of the way we want it to. So, you know, we had this repo and we started running, and we're running our CI build in GitHub Actions, which I'm sure many people are. And we're on the free tier because we're an open source project and we're cheap. And our build uses plenty of stages to try and do that structure that I showed you. And about 10 months ago, our builds were taking in the region of about 45 minutes or so. 9 months ago, it had ballooned to 2 hours. And the reason why I did that is because we realized that we needed to test a few more scenarios, a few more browsers, a few more things. And that has been really useful because now we're testing with the dev and beta releases of browsers. We find bugs before our users do, where people have made changes to the Chrome driver or the Gecko driver, whatever. We feed those back to Google, Mozilla, whoever it is that needs to hear it, and those bugs get fixed before they hit everyone. So it's really useful to be able to do that, but does cause our runs to take quite a long time. And we kept on adding things. And about 7 months ago, it wasn't unusual for us to take about 5 hours to complete a single CI run, which was absolutely unconscionable. Like something absolutely positively had to change. Like we couldn't carry on like that. I'm sure like everyone has been in a situation like that. So how do we fix this problem, right? Well, part of that depends on how we actually build Selenium itself. So this is going to be a bit of a digression, but it's an important one because the way we changed our CI and the way that you can change yours really does depend on it. You will be pleased to hear we are not applying machine learning or AI or any fancy technology that is out of the reach of the mortal man. We're going to use something very new, but mundane. Allow me to introduce Bazel. It's a polyglot graph-based build tool. Oh, that's a heck of a mouthful, isn't it? Allow me to explain that a little bit. Polyglot, it handles multiple different languages. Graph-based, all builds are actually a graph, but Bazel reifies that graph. It makes it obvious and easy for you to use and manipulate and query and do interesting things with. Bazel itself is a tool that is ultimately derived from Blaze, which is the internal build tool at Google. They open sourced it shortly after Facebook open sourced Buck. And of the new generation of build tools that are out there, Pants, Please, Buck, Buck 2, and Bazel. Bazel is the one that has momentum, and it's the one that people are more familiar with. If you've not had a chance to look at it, don't worry, but you can now go to Stack Overflow. There are people who can answer questions. So what makes Bazel different and why did we use it? Well, sorry, there's a dad joke on this slide. It's obviously a hermit crab. I apologize. it does hermetic builds. Now, if you've used, I don't know, Node or Maven or Gradle or Cargo or Pip or Bundler or basically any build tool out there, you will be familiar with the fact that when you start the build, you've got a list of your dependencies and those get downloaded off the internet. It might be jars, it might be libraries you depend on, all sorts of things. So great. But Bazel sort of turns that knob up to 11, that dial up to 11. And what it does is it downloads entire tool chains. So if you want a particular version of Java, you say that in your Bazel build, and that version of Java will be downloaded. If you want to use a particular version of Node, that particular version of Node will be downloaded. If you want a particular version of Rust, that particular version of Rust will be downloaded. It leads to a really nice developer experience because you clone your repo, you do like Bazel build, and although, yeah, it does take a long time to download hundreds of megabytes of dependencies, you don't need to have installed Node, Rust, any of the tools you're going to be using. They just get downloaded, they get made available. And that's really nice because you have far fewer works on my machine problems, right? And that's super important because it means that we can start debugging things more easily. The other thing that makes Bazel different is it's a functional build tool. So it uses this concept of pure functions. So each thing that you build in Bazel is treated as a pure function. Like, what is a pure function? Now, if you haven't gone to university and studied computer science, or if, like me, you forgot exactly what that meant, a pure function is simply a thing that transforms its inputs and provides the output, and it always returns the same output for the same inputs. Doesn't matter what machine you're running it on, doesn't matter how you're doing things, for the same input, you get the same output. And that's super useful because it means that you can now start caching. So you can take a look at all of the inputs that are going into a particular action. You can hash them or do whatever it is. You can work out a key. And if the key is the same, then you know that the output will be the same. And so you can use a key value store to store the outputs. The other thing that this means is most build tools are task-based. So you may be used to the idea of like, every build I want to increment this counter, or I want to do this thing every build. That's not how a functional build works. A functional build will go, the inputs haven't changed, therefore I can use the same output. I think of it as the difference between imperative and functional programming. And like I said, Bazel exposes build graphs. Now, all build tools construct graphs of actions to perform. Like, that's just the nature of the beast. Often that graph is topologically sorted. That means that sort of actions with the fewest dependencies are performed first, and those with the most perform last. And they typically are executed more or less linearly. But like, no matter what tool you're using, the graph definitely exists. But if we could query the build graph, and Bazel lets you do this, if we could do this, we could probably use it to answer really interesting questions like, if these files changed, what needs to be rebuilt? Well, let's take a look at some examples. So in this graph here, we have changed the file in green. Just looking at this, it's pretty clear what we would need to do in order to verify that our build was correct. We just take a look at those files. Similarly, if we were to change this file here, just looking at this build graph, we can see that there's a whole bundle of stuff that we need to do in order to validate our build, and it's those three actions. If we add a new file onto our build graph, there we go. If we add a new file onto our build graph, what do we need to do? Again, we just look at our build. It's this. All pretty simple, right? That's just information that is buried in the graph. And finally, if we were to remove a file, if we took something out of the build graph, what would we need to do in order to validate that our change was safe? Yeah, you guessed it. We'll just build those. It's a super useful idea and concept. So it's a really poorly kept secret in computer science that graphs make it really easy to figure out tasks that can be performed in parallel. Just walk the tree, gather things, and away you go. Bazel is a graph-based build tool. Bazel builds run really fast locally. Part of that is because it interleaves building and testing. That is, tests start running as soon as their dependencies are compiled, not before, and it doesn't wait. So as soon as a test is ready to be run, it starts running. Quite a lot of other build tools have a traditional phase where they do a build, they stop and think, and they start running tests. That wastes time. So by interleaving things, we go faster. Why does it start doing that? Well, because to Bazel, a test is just another kind of action. It's just another step in the graph of what we're doing. So one of the other things is we know all the inputs that are going into each of our actions. We have listed them in exhaustive detail to the point where the build tool can download everything it needs off the internet onto your local machine in order to do it. But if we've listed the inputs so clearly, do we need to run the build on our own machine? I mean, basically each action is like, get these inputs, lay them out on disk, run a command, gather the outputs, and then use the outputs. And we know that we're dealing with something that is using pure functions, so same input, same output. We know that we can store those in a key value store. Like there's nothing tying us to our machine anymore. And that's really important because most of our build graphs are shallow but wide, by which I mean there are a lot of things that need to be compiled all together, but there aren't that many steps in the graph. As an example, if you're compiling a C++ library, each C++ file must be compiled to a .o file. And then once those .o files have been gathered, we gather them together, we link them, and we get a .a file at the end of it, right? So we could distribute that across a lot of machines. And that means that the critical path is now the constraining factor. So distributed builds mean that build and CI time become constrained by the critical path through the build in the ideal case, which is kind of exciting, right? And then if we have a distributed cache as well, then the CI build can use that because it's pure functional. Same result, it'll be fine. So all of these machines running in parallel can all talk to the same cache and suddenly even faster builds. Now, running a build grid sounds like a really difficult thing. And fortunately, we don't have to do that ourselves. On the Selenium project, we have partnered with a company called Engflow, who was set up by some ex-Google engineers. They are fantastic people, really friendly. They've been incredibly supportive and have given us access to a cluster for open source use. It's been a game changer, and I will explain a little bit more in a second. But if you don't want to go to a company such as Engflow, BuildBuddy is another, there are open source tools that you can download and start running yourself. So you can start running distributed builds if that's what you want to do. To be honest, our experience at Facebook was that just having a distributed cache that was shared by everyone was actually super, super valuable. So now we know how we build Selenium and the technology we used. Like, how have we improved our CI times, and how could you do the same? Look, we don't like slow builds. We don't trust them. They're not good. There really has to be a better way. Like, people not using Bazel might want to apply, I don't know, machine learning or AI to figure out how to prioritize tests. But why do that? There must be something simpler. I'm a big fan of not being clever, and well, we're not clever. This is what our new CI pipeline looks like. What we do is we clone the repo, and then in parallel, we do some out-of-band checks, and then we test everything that we have in the repo. I think we can all agree that is a lot simpler than what we had before. How could this possibly be better? Well, the out-of-band checks are for things that Bazel aren't very good at, in particular, whole repo operations. So things where we scan the entire repo. To be fair, for us in the Selenium project, there's just one thing which that is, and that's code formatting. So we have a step that runs all the code formatters, Java, Rust, build files, you name it. And if we have discovered any changes after running the code formatters, we fail the build. The other step that we do, which we can do in parallel, is test everything. Our new step uses Engflow, uses Bazel on the distributed environment, and it runs every test we can on Engflow in parallel. Now, there are about 100 workers, I think, in the cluster we're using, so we can run up to 100 tests in parallel. which is way more than we could do on even like the beefiest machines. And don't forget, we're running on GitHub Actions, so these machines are puny. Now, also, what we're doing here is we're running tests that used to be in their own workflows. So we used to have like dozens of, not dozens, but quite a few different things, and now we just mash them all together. In order to maintain stability, we have a block list of tests that we know to be troublesome, and we allow tests to retry twice. And then the final step of our build is, after running all the tests, we make sure that all the things that we deploy to people and we give to people, so the jar files, the NuGet packages, the Python wheels, we make sure those build safely and cleanly and properly. So nothing rocket sciencey, but it is all quite exciting. So, like, what benefit do we get from this? Well, remember before, the equivalent test runs were taking up to 5 hours, and now they're comfortably under an hour and frequently take less than 20 minutes. And the reason why they're able to do that is because we're using the distributed cache. And when we say run everything, what happens is Bazel uses a build graph to figure out, like, what's the minimal amount of stuff that I could run. So it just runs those tests that are affected by any particular change, even though we have told it to run everything, because it knows that those previous results are unaffected, so it can just return those same ones. So our RBE build times are so much faster. It's extraordinary. And I know that diagram that I showed you looks like it was simplified. Allow me to show you the GitHub action that we have. You can go to Selenium on GitHub and take a look at our actions. This is the RBE build. You'll see it's just those 2 steps that we run in parallel. This is from a recent run. You'll see that the linting took 2 minutes, and running every single test in the repo, and there are hundreds and hundreds of them, took 38 minutes. And that's because we changed something in the Java tree. And when we do that, we actually do need to do quite a lot of work. One of the nice things is, because we are running our tests on NGFlow, they can give us some analysis and insight into how our tests are running and where the time is being spent. And so here is something that from their dashboard. This dashboard is linked to from the logs of our GitHub tests, so we can see everything that we need to. We can go digging in. We can get like nice test failures and stuff like that when something goes wrong, and we can do some analysis of how our build was when things go right. I'll be honest, like, not everything builds remotely. So what's happened is, as we have started pulling things into the build running on NGFlow, our RBE build, our remote build environment build, and we have taken them out of the previous workflow. And so this is the CI workflow as it is now. Remember, this used to take up to 5 hours. It took an incredibly long time. It is now running sometimes super fast in a minute, but frequently in under an hour. It gets far more comfortable and far more useful for us. And particularly in an open source project, when people are working in their free time, taking an hour to do a CI build isn't perfect, but it's a lot better than what we had. So in summary, like, the secret sauce is Bazel. Bazel allows us to query our build graph and only build the things that have changed. And by using remote execution and caching, life is a lot better. Pervasive caching allows us to share our repo with more people and to allow our CI builds to continue using the same artifact every time. And because it's using a pure functional approach, we never need to do the equivalent of a Bazel clean or a Maven clean. We can just keep on reusing that. Remote builds allow us to test everything and expect it to be fast. And it does that because not only is it using the cache, it can run lots and lots of things in parallel, far more than you can on the local machine. The combination of this has allowed us to drastically decrease our CI time. We haven't had to rewrite our tests. We haven't done a huge amount of changes, but we've managed to slash our build time from 5 hours to under an hour. And we could go faster. There are things that we could do in order to squeeze a bit more performance, but we haven't needed to do that. Of course, it's not all been plain sailing. There have been problems. The biggest one is Bazel. Like, it's new. Not everyone is familiar with Bazel. It's a problem, right? And when everyone gets presented with it, not everyone likes it. There are people in the Selenium project who aren't happy about using Bazel because it's not the native toolchain for what they're doing. And worse, not everything builds with Bazel, so we have to fall back to the pipelines that we had. The other thing that I worry about is as we add more tests, that test on Engflow, that RBE build, those times are going to get worse. There's nothing we can do to avoid that. However, if we carefully structure our repo, we might be able to avoid some of the damage. And if we can't do that, then we can do a thing called target determination, where we actually ask Bazel, like, between these two between these two Git revisions, which targets have changed, and we just run those rather than telling it to run everything. That will make our build faster. And now, I hope that we have some time for any questions that are left over. I think that was about 25 minutes, so I think we've got about 5 minutes for questions, if I've got my timing right.
Yep. Simon, can you stop sharing your screen and I'll get pushing the questions on stage. Awesome. Great session, by the way.
Pleasure.
Yeah. First question is, can this be applied to repos where the code and testing cases aren't in the same repo?
I mean, so Bazel is just a build tool. So if you can build it and you can run your test, then sure, you could apply that concept. The only problem is that when something goes wrong in the repo, if a test fails, then your feedback loop will be longer. If you first need to get a change into the first repo and then get that committed and then run your tests against that second repo, right? So your feedback loops will be longer, but there's nothing technically stopping you from
not a bad practice. Is it a good practice, bad practice? Depends.
I am a huge fan of mono repos. Like, I believe in one repo to rule them all, and in the darkness bind them. And so, like, I would always encourage people to put things together. I know that mono repos are out of favor with some people, like they're quite worried about them. So the other thing that I like to do is just co-locate things that belong together in the same repository. So if you've got like some protobufs and you've got some services that use those protobufs, put them in the same repo. Like, separating them out just makes it so your feedback loops are longer, and your life is a bit less pleasant.
Awesome. Great advice. As part of your CI testing, do you prefer test coverage over test confidence to deploy the application? What about experiments? Is it the same rule of thumb?
So for me, test coverage is a way of identifying negative space in your build, right? So it will tell you that a test hasn't been run on this particular part of the tree. It doesn't tell you the quality of the tests. It doesn't tell you actually very much about the quality of anything, right? So coverage is like a number that goes like, something has gone through here, it's fine. If you have low coverage numbers, it probably means that you haven't got enough tests and you should increase them. But for experiments, so coverage for me is just a number. I tend to be a big fan of push on green. Like, when the build goes green, push it live, and away you go. And then as you find problems in production, what you do is you write a reduced test case to demonstrate that problem so it doesn't happen again. And over time, your suite of tests becomes better.
Love it. All right, time probably for one last question. To clarify, Bazel has the ability to map test cases to what has been changed?
So Bazel has this concept of the build graph. So your library, your test depends upon a library, and that library depends on another, and so on and so forth. So you've got that tree structure. And so when you change a source file here, you can just query the tree and go, okay, these are the nodes that have been affected by that particular change. And some of those nodes will be test nodes, and some of those will be, nodes that build a binary or build a wheel or whatever it is. And so when you say to Bazel, like, to Bazel test, it'll walk through the tree, find the nodes that have been affected by the thing that you have changed, and just run the test for that. We in our build say test everything, and we rely on the fact that we have this distributed cache to not test everything, just test the things that have changed between two builds. I hope that makes sense.
Absolutely. Brilliant as always. Thank you so much, Simon. Thank you for contributing to Future of Testing again. Really appreciate you and all you've done for the community.
Thank you very much. It's been a pleasure to be here.
See you later. Cheers.
Cheerio.